Alrighty, welcome back to operating systems. So, lab 3 is now out, so hopefully you have learned something from the labs and time management maybe. So just as a guideline, the labs are meant to be like 10 hours if you have 2 weeks, since 5 courses, 8 hours a week per course, -3 for lectures, so you have like 5 hours a week. So the labs being 2 weeks means you should spend around 10 hours, 8 to 10, something like that. So it seems most people fell within that ballpark. But if you didn't listen to me and didn't, check for errors and immediately crash, you might have spent like 8 hours debugging a single thing. So listen to me. So next lab should be a lot easier. The code is like, if you are good at writing concise code, you should have it done in under like 80 lines, something like that. And it's mostly thinking. You won't have to deal with threads or processes or anything like that. You have to deal with page tables. So you should be able to start it after today. So page tables, always fun. So how we left off on Tuesday, if we remember, we just had this gigantic page table full of page table entries, and that is how we actually translated virtual addresses to physical addresses. So that page table was absolutely gigantic. It was a gigabyte, which is not something you want, a gigabyte page table per process. So let's brainstorm together. What should we do about this page table size? Because most programs don't use 512 gigs of memory. Your programs probably use like a few megabytes or something like that. So what should we do in order to not have a gigabyte page table? Any ideas? Yep. Use a hash? Oh, use the cache? So a cache just makes lookups faster. It wouldn't reduce the number of entries we have. So it still would be a gigabyte. Yep.
Make a page table fit on a page.
Read ahead a lecture, make it fit on a page. Or in general, just make it smaller, right? I can just make it smaller. So if I just make it smaller, that's a solution. So if I made it such that one nice thing to do would be just make it fit on a page. We'll see why we do this in a little bit, but turns out that a page is a nice number. Your operating system can just allocate pages, nice and easy. So if we only had a page for a page table and we try and make it fit on a page, well, we can do some math and work backwards. So our pages are to the 12, so that would be the entire size of this page table. And if our entry size is 8 bytes, which is 2 to the 3, then I can fit 2 to the 12 divided by 2 to the 3 entries in this page table, which would be 2 to the 9. So I would need 9 bits for my index, and then that's it. So now my page table is only 4 kilobytes here. And when I'm translating the address to MMU, all you have to tell it is where to start, where the page table is physically located in memory. So there would be a register that says where your page table is, and that would be a physical address. And then in this page table, it would look it up, do the same translation we did before, but instead of 27 bits, now we only have 9 bits. And here the physical address would still be the same because our page table entry is the same deal. Everyone on the same page for this one? Yeah?
Wait, how is it like less entries but like the same amount of like output?
So this is not the same amount of output. So I can only fit in 2 to the 9 entries in this case if I make the page table small enough such that it fits on a page. But everything else stays the exact same as we had before. All right, so we're good so far because, yeah.
How do we know that's enough for our process or program?
Yeah, so the next obvious question might be like, well, so 2 to the 9 entries, if each of those represents a page, then my program can only use at most like 2 megabytes of memory. So what happens if I need more memory? What about if I have a program that actually wants to use all 512 gigabytes or a gigabyte or something like that? And that leads us into our solution, which, get ready for it, because this is where everyone's brain starts to break. That is our solution. So we have multiple levels of page tables, and we will spend the rest of this lecture talking about this. So how this works is it has the same idea where you just kind of cascade a bunch of smaller page tables that fit nicely on a page all together. So up in the virtual address before we had 39 bits. Now if you add all of these together, you get 39 bits. So luckily our offset doesn't change. It's related to the page size. We're not changing the page size at all. So it is 12 bits, and in L0, one of the lowest level of page table, it is 9 bits. So that's just because it was like before, we want to fit each level on a single page. So here, if you count up the number of bits, we have to have 3 levels of page tables. So now, when we translate an address, this root page table register just points to an L2 page table, and then the only difference in here, this page table is still full of page table entries, but the physical page number actually is the physical page number of the L1 page table. So the entry here tells you where to find the L1 page table. And then in the L1 page table, you take this L1 to figure out what index you need to look at to get the entry. And then once you get the entry, it has a physical page number that tells you where to go in the L0 page table. Once you're in the L0 page table, that's the same as we had before. That page table entry has the physical page number corresponds to the actual physical address of that virtual address you're actually interested in. So, any questions about this? Because this is how your page tables work. Yep.
So the naming scheme L0, L1, L2, that has nothing to do with cache, right? Because cache we also name the same way.
Yeah, so cache is named the same way. So this has nothing to do with cache. They're just different levels of page tables. So they're named the same way. The only thing here is that you might consider it backwards, but L0 is like, that is the page table that has the entry you actually want, like in this step, where we just look it up and we get our physical address directly. So no matter how many levels of page tables, once we get to L0, that will have the actual physical address of whatever we're interested in. Yeah.
So we can only have 2 to the 9 actual physical addresses, which are in the L0 page table?
Yeah, so in the L0 page table here, you can only have 2 to the 9, because it only has 2 to the 9 entries. But in this table, right, it can point to 2 to the 9 things, and then each of those can point to 2 to the 9 things, and then in there, they can point to 2 to the 9 things.
So the idea is we need to be able to map to all 44 bits in the physical address.
So we need to map to the 27 bits for the virtual page number here. Yeah. So we're still representing that 512 gigabytes of virtual memory. And yeah, isn't this just more steps? Yeah.
Could you explain why the L0 is 9 bits for 2 to the 9 entries?
So this 2 to the 9, so all these are going to be 2 to the 9 because we want to make our page table fit on a page. So this 2 to the 9, why there's 2 to the 9 entries is because 2 to the 9, the number of entries times the size of the page table entry needs to equal our page size. So our page size is 2 to the 12, and our page table entry is 9 bytes, or 2 to the power of 3. So yeah, so here you can, here I can write that. So not bold. So if our page size is, 2 to the 12, and our page table entry size is 2 to the 3, which means 8 bytes, well, it means that the number of entries we have that we can fit on a page is equal to 2 to the 12 divided by 2 to the 3, which is equal to 2 to the 9. All right. Yep.
Oh, wait, was that bits or bytes? Because 2 to the 3 bits is like 1 byte, right?
Yeah, 2 to the 3 bits is a byte. So that's 2 to the 3 bytes because the page size is also bytes. Yeah, so this is, the obvious question to this is like, what the hell, isn't this the same thing with more steps? Oh, yeah.
I was just about to say, like, how does this increase the actual number of entries?
So this keeps the number of entries the same.
So then what's the point?
So when we had that big, large page table to translate a single address, how big did our page table need to be?
Oh, okay.
You're
breaking it up into smaller page tables.
Yeah, so before went with one big page table. That one big page table is a gigabyte, even if you just need to translate a single address. In this case, if I need to translate a single address, I only need one L2 page table, which is a page big. Then I need one L1 page table, which is a page big. I need one L0 table, which is a page big. So that would be 12 kilobytes instead of 1 gigabyte. Yeah.
Wait, how does the 9 bits from the L0 page table map to the 44 bits of the page number? I mean the page table entry or whatever.
So inside the page table is just the same page table entry. And in the page table entry, that has the 44 bits, right? Because the page table entry is 64 bits, so it's big enough. So, yeah. Yep.
So if the L2 page table points to an entry L1, and the L1 points to L0, how is it like more, and like, I don't really understand how that works.
How, what works?
Like, isn't it the same thing as just having like a straight to L0 page table instead of like, what does L2 and L1, what does that add to?
So this, we're shrinking this, each of these page tables is way smaller. So each of these is only a page. So the only thing we're saving is space if we don't have to do a lot of translations in a program. So in the worst case, this actually wastes more space on page tables. But we're going for the common case, which is most programs do not use all the address space, right? So in here, in order to translate a single address, we only need one L1 page or one L2 page table to point to one L1 page table to point to one L0 page table. So we only need 3 pages to translate an address. So that is 12 kilobytes instead of 1 gigabyte. So in the worst case, we would have one L2 page table pointing to the 9 L1 page tables if we wanted to use everything. And that would also point to the 9 L0 page tables, and then each L0 page table would point to the 9, and you'd actually waste more space than a gigabyte, slightly more. But the case we're trying to optimize for is most programs. Most programs do not use 512 gigabytes. All right, any other questions? Because we're going over this all day. Yep.
How much slower would the lookup be?
Oh, that is a good question. How much slower would the lookup be? Yeah, so how slow is this? So in order to access memory, how many times do I have to access the page table to actually find my address here? Once, right? I just look it up, so I need, instead of if I was just using raw memory, I would just have one memory access that I actually cared about. For this, I need to look it up in the page table, which is one memory access, and then do my original one. So I'm making it twice as slow over not having one. And then in this case, yeah, you're right, this is way worse. So in order to translate a single address, I have to have a memory access in L2, and then I have a memory access in L1, then I have a memory access in L0, and then I have my original memory access. So I have 4 memory accesses. So we'll address that next time. But the solution is your solution. Just put a cache in front of it. But we'll see that later. All right, any other questions? All right, then we will just hammer this home. So the reason why it does this too is page allocation. If you have fixed size blocks of memory or pages, writing a memory allocator is dead simple. It's just a linked list. So whenever your computer boots up, the kernel can just divide all the memory into pages so that everything is nice and aligned and starts at address 0 and everything. And the operating system just treats them as pages and can create a linked list of all the pages. So initially, every page would just point to the next page over and over again because you're not using any memory at the beginning. And then whenever you want to allocate memory, one page is just as good as any other page, so you can just take the next pointer in the free list, that's just a linked list, get it from the head, nice and easy. And if someone deallocates a page, it's the same thing. It's not used anymore, you could put it at the beginning of the free list, and you can reuse it again. So allocation becomes dead simple once we have pages. We don't have to have some complicated memory management, anything like that we'll talk about later. So dead simple once everything's the same size. So, and yeah, this was our insight, is just to use a page for each smaller page table. It saves us a lot of hassle because you know where everything is on a page. If it fits on a page, everything is the same. It's nice and uniform. You don't have to argue about different page boundaries or figuring out, you know, how big a page table is if it was dynamically resized or something like that. You just grab another page. It's nice and easy. So some people get tripped up on like the size of page tables. It's really easy if you just think of it as an array. So I assume you could do this. So if I gave you an integer array of 512 elements, can anyone tell me how big that is in bytes? Yeah. 512 times 8. Next.
512 bytes, or is it 216?
512 bytes?
I mean 256.
256. 256 bytes?
Because an int is allocated
How big is an int?
4 bytes.
Yeah, an int is 4 bytes. So what is 4 times 512?
2048.
Yeah, 2048. So this is just 2048 bytes. So one question might be also, well, what's the offset of index 2? So offset, remember, is just the number of bytes from the beginning. So at index 0, well, the offset is 0. It's at the beginning of the array. And in this case, since every element is 4 bytes, they're divisible by 4. So it would be like 0, 4, 8, da, 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 da. So at 2, that would just be 2 times 4. So it should be at index 8. So it's the same thing for page tables. Just substitute an int for page table entry. So this would be something you're always given in a question. If you're not given it, a good number, it's 8 bytes. So by default on your system, it's 8 bytes right now. So if the page table entry was 8 bytes and our page, and we had 512 elements, it's the same idea. How big would that be? Well, now it's 8 times 512, so it'd be 4,096, which is, guess what? The size of a page. Everything makes sense, right? So you should also like double check these numbers. So page size was 4,026, which is the size of the page table I got. And remember, size of the page table, it's just the number of things in it or number of entries times the size of the page table entry. So all these numbers should be consistent. If something doesn't jive, you have screwed up. There's lots of ways to double check your answer. All right, let's translate a fun address then. So say we have, let's just write it out. All right, so say we have some crazy address. We'll have the address in hex 3FFFF008. And we will assume that we only have like 2 levels of page tables. So we have an L1 that points to an L0, and then in the L0, that's where our actual lookup is. So if we take our address here, and then divide it up, well, it should be something like we have 12 bits for the offset. And then it's going to be the same scheme. Our page table entry size is 8 bytes, and our page size is at 4 kilobytes. So here, if we write it out, we have 9 bits for our L0, which doesn't nicely go in there, so I have to write it in binary, and then 9 bits for my L1. So, because it's the same thing when we're translating the address, this part, whoops, so this part is the offset. I can just, it's 12 bytes or 12 bits, so I can just keep it in hex. I don't have to translate it, it stays the same. The rest of it, to figure out what indexes I need to use, unfortunately, I have to do something like I have to put it in binary, which for this, luckily enough, everything is just a bunch of ones. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So if we write it all out, this is our L0 index. This is our L1 index. So if you have 9 bits and they are all ones and you want to bring it to decimal just so that we can, I don't know, talk about like actual humans, then this is the same as 512. So that's just 512 in decimal. So in order to translate this address, you would need our root page table in like an SAP register or something like that, and it would just say the physical page number of wherever the L, in this case, there's only 2 levels of page table, so it would say where the L1 page table is. So it would say something like, I don't know, say it's at physical page number 7. So if it's at physical page number 7, that means our fancy L1 page table here, it means it starts at address 7000 because that would be the beginning of a page, and it would go to address 70FFF. So you don't need to tell where to go because it fits on a page, has 512 indexes, so it uses the entire page. And to double check, if you do that math, whoops, if you figure out what this address range is, well, you know, it's 1000 in hex, which guess what, is 4096. So everything kind of makes sense. So in order to translate this address, there would have to be an entry in this L1 page table at index 511. So at 511, there would need to be a page table entry. I'll put some columns here, like the physical page number, and then like a valid bit or something like that. So in this entry, the physical page number could be something like 08, and it would have a valid bit, which means it can actually use it. So in that case, what address do I go to access my L0 page table? Yeah. Yeah, so because my physical page number is 8, it means it would start at address 8000 because it fills up a whole page and it goes to address 8FFF. So my L0 page table would be there. And this way it makes it flexible. It didn't have to be right beside it, right? And question? So, could I go over how I drew this page table? So I just draw the page table that every row inside of it is a page table entry, and I just write the index outside of it because it's not stored in it, just to the left. So I just show it what the index is, and then each row in this page table is a page table entry. So in order to translate this address, there would need to be something at 512, and then it could have a physical page number of something like CAFE with a valid bit, in which case, if that is what is there, then I could translate the address. So I keep the offset the same, so my physical address, well, I would keep the offset the same. The offset is 008. And the physical page number just comes from the L0 page table, whatever the entry is. So my physical address would be CAFE008, and that would be my physical address. So any questions about that translation? Yep.
Which entry was 0x8 from the L1? How did we find which entry that was?
So we found what entry that is, but from the L1 part, from the L1 index of that address. So like it was the same thing here, except we didn't have an L2. So we had a 30-bit address, so we only had up to L1 here. But you can see how this gets extended. So you could have a 30-bit address, that's one. If we add another page table on top of it, it's 39. Then the next extension is if we have 4 levels of page tables, well, the next size of virtual address space we can have is 48 bits. So we just add another level on. Yeah, and then we have a question, what happens if V is 0? So V is 0, which is the valid bit. It means this entry is not valid, so that's when you would get a page fault, or like you can't access the memory, your process just, if you guess a random address in your program and try and dereference it or something like that, you're gonna get a seg fault, which segmentations don't exist, but it's basically just a memory fault. You're accessing memory you're not allowed to have. So that would just, by default, if there's no valid entries, it'll just be 0 and it'll just fail the translation and your program will probably die. All right, any more questions about that? Okay, we can translate address. That was 2 levels. Doing it another time isn't too bad. And doing it a 4th time, not too bad. So in this case, the savings aren't that big if we had a single, like if we had a 30-bit virtual address and we just had one giant page table, well, then we wouldn't split it off. We would have 2 to the 18 entries. So that would be 2 to the 18 entries if we just had a giant page table, and then each of our entries are 8 bytes. So in total, we would need a 2 megabyte you can make up numbers. That should work. Yeah. Okay, so that was only 2 page tables, nice and small. And that's it. So we can have an example that we can play with and we can understand. So we can play around with stuff to see, and this will be closer to lab 3. So any questions at all? Because usually people are like, have no idea what the hell is going on, but hopefully that was slightly clear. Yeah?
So I would just assume that initially everything in the L1 table is pointing to like a single L0 table, and when the L0 table fills out, then another L0 table will be created, and like entries in the L1 table will be like pointing to that.
So initially your L0 page table, if there's no valid mapping, it would just be full of invalid entries, and then if the MMU tried to translate it, it just wouldn't translate it, right?
Then like if the L0 table fills up, then you'll have like a second L0 table that's being created.
Yeah, so if, so it would look something like this, right? So our L1 page table, these are all the entries. It would have a single entry that points to an L0 page table. And in here, you know, it would have 512 entries. And eventually, if this all fills up, well then we have to put a new entry here that points to a new L0 page table. Whoops. And then it can hold more entries, right? And go on and on and on. And then, of course, I could have, whoops. I could have 2 to the 9 of these, right? I could point to 2 to the 9 L0 page tables. Yeah.
So when you were saying that you have a 4 kilobyte L1 page table and a 4 kilobyte L0 page table, in that particular instance, there's only one L0 page table?
Yep. Yeah, to translate a single address, I just need one L0 page table. So if I had to translate 2 addresses, it could be like you said, and they're beside each other, and that would be nice because I wouldn't need an L0 page table. You could also get insanely unlucky because it just depends what the indexes are, right? So I could craft it such that for 2 addresses, they correspond to 2 different entries in the L1 page table, in which case to translate them, I would need 2 L0 page tables because they don't correspond to the same one, right? Yeah.
So if like a program is running and it used all of the L1 entries, so you have like 2 to the power of 9 L0, does it add like a lower level, like N-1 table?
No, so it would just, so like the indexes just need to line up, and your operating system, if that's a valid address, just has to make sure that it can follow the page tables until that address is valid. So here, we can do an example too. So we have a little simulator, and guess what? That's what Lab 3 is anyway, so we may as well see it. So in this case, let's make this bigger. So here I just check if the page size is what I expected it to. And here in this allocate page table, all it's going to do is give me a page that I can put whatever the hell I want on it. And otherwise, there's just a bunch of little macros to create page table entries for you. So this is a pointer to a 64-bit entry. So the page tables, they're just 64-bit numbers, 8-bit numbers to correspond to the page table entry. So here I create a new L2 page table, and then the MMU, right, the only thing it needs to start off the translation is it needs a root page table, which would be an L2 page table if I have 3 levels. So if I have 3 levels, I have to tell the MMU what my root page table is, so it can start off using that for the translation. Then past that, it just follows the levels until it translates the address. So I tell it what it is, then I create an L1 page table, and then here at index 0 of my L2 page table, I create a page table entry to essentially point to that L1 page table. So this is, and this macro just plays with the bits in order to get, essentially extract out the physical page number from that address and does that for you. Then here I have to create a L0 page table, or an L0 page table, and then in my L1 page table, I just pick index 5 because I felt like it, and I make it point to an L0 page table. Then the L0 page table, I create something at index 188, and then this is where I put in the physical page number directly. So it doesn't play with, doesn't assume that that address is a page, it just uses it directly. So, yeah, and then another question, do programs fill by row or randomly anywhere? So ideally, if the addresses are right next to each other, that would correspond to addresses that are sequential, right? The pages would be the same, so they would be next to each other in the L0 page table, which is good because we wouldn't be making a bunch of page tables if we don't want to, right? So that would be good. So in this case, I'm going to translate to virtual addresses. I don't know why that looks weird. Okay, my shell died, cool. So if I do that, I get a valid translation, and I get a page fault, which just means that it couldn't translate the addresses. Yep.
Did you write the functions like allocate page table and the other ones, or is that like available from like C or Linux?
No, so those are little helper functions. So you'll have the same ones available to you in Lab 3.
You wrote them, right?
Yeah, I wrote them. It's essentially simulating that free list thing, although it just asks the kernel for memory. So the kernel does it. All right, so can we figure out why this translated properly and this address did not translate properly? Yeah.
You actually if page numbers are assigned at random, you actually assign a page number to cafe, to C-A-F-E, in the reverse direction, you mapped A, B, C, D, E, F to an L0 table to an L1 table to an L0 table, which maps to CAFA, but you didn't do the same for the other one?
Yeah, well, let's see. So if I were to translate the address A, B, C, D, E, F, that's as far as I know my alphabet. Thankfully, I work with computers, so I don't need to know any more than that. So if we had this address, A, B, C, D, E, F, and we had 3 levels of page tables, well, it would correspond to the same thing, right? We have, in my virtual address, I would have 9 bits for L2, that index, 9 bits for L1, 9 bits for L0, and then my offset is going to be 12 bits. So again, I do not have to translate DEF, and then for the rest of it, I can just write it out in binary because that's the thing we have to do now. So what's A in binary? Do we remember our shortcut from last time? Yeah. 1010, 1010. All right, so A is 1010. Do we know what B is? Can we add 1 to it? 1011. And then adding 1 to that again, 1100. So that is ABC in binary, and then I have to group it in groups of 9s. So that's 4, that's 8, and this is 9. So, and then of course, there's a bunch of leading zeros all over the place. So in this case, what would my L2 index be? 0. What would my L1 index be? 5. What would my L0 index be? 188, hopefully. Well, it worked, so it must have been that. So that's why that address translated successfully, because given a virtual address, I know what entries I need to make valid in order for it to translate correctly. So my L0 page table, that's where the MMU, like that was given to the MMU, and then how the MMU translated it, it looked for entry 0 in the L2 page table. So at entry 0 points to L1, and then in L1, given this, it would have looked at index 5 to find the L0 page table. So it pointed to this page table, and then at 188, mercifully, it had an entry, so that's why I was able to translate it. All right, well, what about if I wanted to do, let's do a brain buster. So what happens if I put an entry to there? So what address would I need to have to use that? Yeah. Yeah, instead of A, B, C at the beginning, it should just be A, B, D. Right, I'm just increasing it by 1, same as going to the next index. Same thing. So if I do that, hey, I get 2 different addresses that correspond to the same physical address, which is fun. Isn't that fun? Yeah. Isn't that a problem? That is a good question. Is it a problem for you? Yeah, it's sometimes a problem, but sometimes this is useful. So you can ask the kernel nicely to do this in 2 different processes, and you can share memory between them and then communicate like that, which is pretty fast. There are other reasons to do this, even though you might think it's a bad idea now. But if you get into research or like you get a job where you have to be a wizard, this could be useful. So we'll figure out ways to play with this. But any questions about this? Because this is fun, right? Yeah.
Can we go over the last bit of the example where we're like after we grouped the ABC to lines and how? So what is the 5 is the index at L1?
Yeah, the 5's the index at L1. So if I just go backwards, this is my L0 index. This is my L1 index, and this is my L2 index. Yep.
So the reason, like, the offset is just the starting address for the L0 index. No, it's the starting address for the physical page numbers, no? Is that why we don't care about it?
So the offset is just where you are within a page, right? So you don't have to translate it because it's going to be the same. And I don't need an offset or anything when I am pointing to the next page table because it always starts at the 0 boundary and it fits exactly on a page. So if I need to index something, I know where to go. I don't need an offset. My index is given to me by the virtual address, and then if I know the page entry size, I know where to access memory to find it. Yeah.
So, like, here we're given a virtual address, right? So how does the kernel, like, assign a virtual address to certain memory?
Yeah, so that's the question. So here we're given a virtual address, and then the question might be, well, how does it figure out what virtual address you need to start anyways? So if we remember back in lecture 2 when I made that example, you hard code the address. So I had a starting address there, and if you remember, I told you I just picked this for no reason. So I picked it for no reason. That was true because it's a virtual address, and then it's the kernel's job to map it for me. So the kernel figures it out for me. So yeah, you having the problem of given a virtual address, you need to figure out which page table, you have to figure out the page tables and get memory for, that's the kernel's problem. So a lot of your programs will just, like your global variables, minus some compiler options, will basically, the compiler will just pick a virtual address for you, and then the kernel has to figure it out. So this is how it works. And you can do lots of fun tricks with virtual memory that we'll see later too, because, hey, you can just arbitrarily map things to whatever you want. All right, any other questions? Yeah.
So when we made that number, we started with A, so that's like 1, 0, 1, 0. Why did we add 3 zeros before? And like
Oh, so the,
the 9, is that like an X, the first 0, 0, so it's 8?
oh, so here, so this part is like the offset, so I don't need to translate that, I don't need to do anything with that, right? Then here, I just wrote 8, so up to here, this is A, B, C in hex, right? And then above that, it's just like if we were doing numbers in decimal or whatever, there's implied leading zeros there. So in this case, it's like a whole 39 bits, so it would be like a bunch of zeros. Everything else would be a 0, right? It's just, I skipped a few numbers. So it's just leading zeros, everything would be a 0 just by default.
And then why did we just pick like 4 bits for L1 index?
Oh, yeah, so I just shortened it. So this would technically, if I wasn't as lazy as I was, this should be 0, 1, 2, 3, 1, 2, 3. So I was just,
9 bits.
yeah, 9 bits, and then this would be 9 zeros. I just don't want to write 9 zeros. All right, any other questions? All right, well, lab 3 is you're essentially copying what is going to happen on a fork. So if a fork happens, well, if you just copy all the memory, you have to copy the page tables, and then for every bit of memory it's pointing to, you have to copy the page and make it point to a new page, and then copy all the memory. So in order to implement a fork, copy all the page tables, and for every entry, you point at a new address and then make the 2 pages the same. And then they're the exact same as the fork, but independent. Same virtual addresses, same everything. Different physical addresses. Lots of fun. So, good. Ish. I see concerned faces, I see ish faces, I see whatever. All right, well, we have time left over, so, well, we don't have that much time, but start working on the lab S questions. So this lab is mostly figuring out what the hell is going on, and the actual code you have to write isn't that bad. This one's more thinking. So don't worry about whatever the hell happened in lab 2. You get to revisit that pain again in lab 4. So, yeah, we haven't hit the hard part of the course yet. We're like, this is, at least in my experience, the second hardest thing. Yeah.
Will the solutions to the lab be posted?
No, but you can come talk to me about them or whatever if your thing doesn't work. Or I can spend, yeah, I can't post them because I have to reuse them and it's a thing. Yeah, I can do something with it. I can either just answer questions of people or just do a non-recorded thing where I just go through it. I don't care. All right, cool. Just remember, pulling for you. We're all in this together.